Hello everyone. So today I wanted to show you how to do a correlation and simple linear regression in Excel. However, both of these analyses are pretty fast and easy to do in Excel. So I also wanted to demonstrate how to do these analyses in R. So to begin, I kind of want to give you the look of this table that you already seen before, where you have your t-tests, you have your ANOVAs that we spoke about previously, and it tells you what are the requirements for these tests. And today we'll focus on the bottom two, which is correlation and simple linear regression. An important thing you notice when you, oh, what happened? Important thing you notice when you look at both of these statistical analyses is that you have your correlation with two dependent variables. And you probably heard that correlation does not equal causation, and that's because you have zero independent variables for this statistical analysis. So you're just looking to see if as one variable increases, is the other one going to increase or decrease? And therefore, you only have your two dependent variables, and they're both continuous or ratio. For your simple linear regression, on the other hand, you do have your independent variable. However, unlike t-test or ANOVA, where you have more of like binary categorical data, you have to have also continuous or ratio. So you have a predictor and an outcome in a regression. So one variable predict what's going to happen to your another variable? So with that being said, I just wanted to show you a few examples. So for correlation, the example is that the researchers want to see if there's a relationship between tumor necrosis factor alpha in plasma, which promotes inflammation, and microRNA 424 in lymphocytes, which has been shown to protect against stroke through inhibition of microglia proliferation. So in this case, we have tumor necrosis factor alpha and microRNA, and both of these are continuous variables. So we're just trying to see if there's a relationship between them. And here's the data that I have. This is your correlation for TNF alpha and microRNA. And you can find a correlation using the data analysis tab, like you did for the previous test. You find the correlation, then you click OK. And then for your input range, you're just going to select both of your columns with the data. And then we identified that it's grouped by columns. I did select the labels, so I want to make sure that the labels are in the first row. And for output range, you just click that and you click any cell where you want your output to be. You click OK. So as you can see, you have your correlation over here, which is a strong negative correlation. I'm pretty sure the cutoffs are 0.7 to 0.9 or 0.01 is the strong correlation. Below, like between 0.5 to 0.7 is moderate, and below 0.5 is a weak correlation. However, you can also double check about that. I'm not sure if that's the actual cutoffs, but I'm pretty sure. But you can just Google what the cutoffs are for your correlations. But this is definitely a strong correlation, and it's a strong negative correlation. However, you can see that we don't have a p-value with that. So we don't know if this correlation is indeed statistically significant. So I'm going to show you how to find your p-value using Excel. So you click equals. So the first thing we actually want to do is we want to find our correlation coefficient. It's going to be the same coefficient as here, but I just want to show you how to use the formula to actually find it. So you click equals. Then Pearson is the correlation coefficient we'll be using. There are other methods of finding correlation, but I'll be using the Pearson's R. Then you select both of your columns. So that you select the first column, comma, and then you select your second column. Do not select the labels in this case. You click OK or Enter. As you can see, it's the same value, and that's the formula that Excel is actually using when you click that data analysis to find your Pearson's R. Next thing you want to find is your N. N is your total number of observations. You can either count it or you can just write equals and then count, double click, and then you just put the number of observations. It's going to tell you 15. Then we find our degrees of freedom. Degrees of freedom for correlation is N minus 2. So we do 15 minus 2. And then the next thing we want to find is T statistic. So the formula for T statistic is on Google as well. So, don't worry if you forget it. It's just a formula for a mathematical equation. You click equals, open parentheses, your correlation coefficient, multiply by the square root of your degrees of freedom. And you close the parentheses. Then you divide that by the square root of 1 minus your correlation squared. You close parentheses. Okay, so this is our t-statistic that we get. And we can actually find a table on Google, which will show us the p-value, which is attributable to that t-statistic. But I'm not going to show you that in this video. I'll just show you how to calculate the p-value from Excel. Calculate the p-value, you click equals, t-distribution, t-dist. Then you select your t-statistic, then comma, your degrees of freedom, and tails. Important thing to notice here is when you do that, it's going to give you an error. And the reason for this error is the fact that our t-statistic is negative. And if you want to prevent that error, you just rewrite your t-statistic, but you just remove the negative sign. So it's 11.18. Click OK. So this is your p-value. As you can see, the p-value of 4.7 times 10 to the negative 8 is statistically significant because it's less than 0.05. So we can say that this correlation is indeed statistically significant. And if you want to insert a graph, you're just going to select both of your columns. And you're going to insert a scatter plot. And then here, what I like to do is, of course, add. Oh, wait, hold on, what happened? Is I like to add the labels. But another thing that I like to add is I like to click on the plus sign and add a trend line. And with the trend line, if you click on this little arrow, more options, you can display the R squared and the equation on the chart. Okay, so this is going to be your correlation, and the R squared is basically how close are your points to the best fitted line. And the maximum is 1, -1, or +1. And in this case, your R squared is pretty close to 1, so that's good. Okay, so that was the correlation. Now I want to go back to the example with regression. So this is our example. Scientists are trying to see if TNF-alpha inhibitors are related to the increase in the BMI. So we go back here. This is the data that I have. And to do a regression, you're just going to select, you're going to click on data and then data analysis. And then you're going to select regression. So input in Y range is your first column. And make sure actually that for your Y is going to be your dependent variable. So in this case, I actually want to choose your BMI as a dependent variable. And then X range is going to be my independent variable. And then labels, because I did select the labels. And output range, again, just click somewhere over here. There's a lot more things that you can display, but I'm just going to show you how to get a simple regression output. Click OK. So then multiple R squared, this is what you really want to focus on, as well as your significance, your p-value, which is right here. So your multiple R squares is basically your correlation. So how are they correlated between each other? The R square is how much one is able to predict the other. And the adjusted R square is if you're going to have more than 2 columns, more than 2 variables, you would want to use adjusted R square because it adjusts the R value based on the number of different independent variables that you have. So in this case, since we only have 2, I would want to use the R square for my results. And the closer it is to 1, the better predictory variable is. So TNF is a good prediction of the BMI because it's very close to 1. And then based on our significance, we can see that it is statistically significant. So that is basically it for the regression. And then you can insert your graph by selecting both of your columns and basically doing the same thing as you did for the correlation. Trend line, more options, equation, and R squared. So this was the regression, and both of these analyses, as I said, is very quick in Excel. So I just wanted to show you a quick demonstration how to do it in R. So in R, I have already the codes saved. So I'll start with correlation. So you have your working directory, which you have to set first. As you remember, I indicated that in the last video as well. your working directory is going to be where you saved your file. And in this case, this is my working directory, so I'm going to run that code. Then you have to read the file that you saved. In this case, I saved my correlation file as the CSV, comma, separated values. So you name your file of whatever you want. I named it CR for correlation. Then you're going to use the code read CSV and write the name of your file, how you saved it in your working directory. And then I want to indicate that I did use the header. Then I say header equals true, and you run that. Then I want to open up the file, so I'm just using the name that I indicated here, so CR. And I just want to make sure everything's correct. So everything looks right. You have 15 observations and 2 different columns. Next, you want to install these 4 different packages, which will help you to do the analysis and also to create your plots. So let me just install the packages. It might take a while. Okay, so once the packages are installed, you want to make sure you pull those packages open so the R can actually use them. So you just write library and the name of the package. Okay, once you do that, the next thing I want to do is I want to create my scatter plot. You can do the correlation analysis first and then do the scatter plot, but I'll just do the scatter plot first. So I'm going to use the function ggscatter, which is going to create a scatter plot, open the parentheses, the name of the file that I want to use, as you remember, I named it CR. So CR, my X is going to be, or my independent variable, in this case, there's no independent variable, so it doesn't really matter what you put for X and Y, but I say that my X is TNF and my Y is RNA, and then I want to add my regression line, and I want to show my confidence intervals in on the graph. I also want to show my correlation coefficient, and the correlation method that I want to use is the Pearson's R. And then lastly, I just want to indicate what I want to write in my X labels. So for my X, I'm going to write the TNF alpha, and for Y labels, I'm going to write microRNA. When you run this, it's going to create a scatter plot like this for you. Okay, and then you can use that in the paper, and you can modify this graph further by changing colors, moving where you want this R and P value represented. But just this is how you create, your raw graph for this analysis. And then to conduct a correlation test, you use the function core.test, and in open parentheses, you indicate your first variable, which is TNF. Then you indicate your second variable, which is RNA. And as you remember, I showed you, you can always just write TNF, this, but I like to write the name of the file and then put the $sign, and it just generates 2 possible columns that I can use. And it just making sure that I won't like misspell anything and that the code will run smoothly. And then again, my TNF, then RNA, and the method that I want to use is the Pearson's R. And I run this and I get the same numbers as I got in Excel, where I have my T statistic, my degrees of freedom, my p-value, which is statistically significant, and my correlation, which is a strong negative correlation of 0.95. Okay, so this is how you do correlation. As you can see, not a lot of things. And the next thing I wanted to show you how to do regression. So you would do the same thing. Your first step, actually, let me click on this little broom over here. That's going to clear up your plots. Broom over here is going to clear up all of the data that you uploaded. And then I also want to click Control and click L, and that will just clean the console. So we just start from the fresh page. So the first step, again, you want to set your working directory where your file is located. Then you want to read that file. I'm going to name my file RA for regression analysis, and I'm going to say read CSV, regression CSV, and then this regression CSV is the name of the file like I have in the working directory. And then I want to indicate that I do have headers in there. You run this, and I just want to make sure everything is correct. So I just run the RA or regression analysis. That's what I named it. And it shows me two different columns with the values. Then again, I have to install those packages. However, since I just installed them in the correlation analysis, I'm not going to install them again, but I will go ahead and just put them out of the library just to make sure that R has them ready. Okay, now I'm going to do the regression analysis first, and then I'll do the scatter plot. So I'm going to name my regression analysis model. You can name it whatever you want. Then I'm going to click that arrow. I'll write that arrow over here. And then LM, open parentheses, your dependent variable, which is BMI in my case, this squiggly line, and then TNF. And then I want to indicate that the data where these labels are coming from, where those data points are coming from, is called RA. And that's what I named my data previously. Okay, then I'm going to run that. And then I just want to pull up that model, see if it did what it did. Okay, I just write model because that's what I named it. And it shows me my intercept, which you can also then use in your paper. But now I want to write summary, open parentheses model, and run that code. And it's going to give you all of the information that Excel gave you, where you have your residuals, if you want to indicate those in your paper. You have your intercept, then you have your degrees of freedom, multiple R squared, adjusted R squared, you have your F statistics, and you have your p-value. And again, all of these values should be the same from your Excel. So if you had a different value, you probably did something wrong. So after you get this and you want to create your scatter plots, you use the function ggScatter, just like in the correlation. You open your parentheses, you indicate the data which you want to use. So in this case, it's RA, comma, your X variable is independent variable, your Y variable is your dependent variable. Then I indicate that I want to add the regression line, I want to add my confidence intervals, I want to add my correlation coefficient, and my correlation method that I will use is the Pearson's R. Then for my X labels, I'll indicate how I want to label my independent variable, and then Y labels is my dependent variable. Again, I run that and it will give me my scatter plot. So we can see as the TNF increases, the BMI will also increase. And so there's a strong positive correlation, and that can be seen from your R statistic here. So we can see that there's a strong correlation based on the multiple R squared, and based on the adjusted R squared, we can see that the TNF is a good predictor of your BMI. Okay, so this was it for the correlation and regression. As you can see, there's not a lot of steps compared to the other tests, for example, ANOVA or independent samples t-test. So if you want to practice that in R, feel free. And if you need the codes that I use, I can definitely send them to you. So just let me know if you have any questions, and I hope this was helpful.